Thank you for the opportunity to present, and good afternoon to all. This presentation is co-authored by my since graduated Ph.D. students, Dr. Samar Yunus and Dr. Haluk Laman. And the title, as you can see, is the truck diversion using real-time traffic data. Don't know if you are aware, but the vast majority of freight in the United States actually moves via trucks or with trucks. Unlike other places, for example, in Europe, where rail is used a lot, here in the US, almost 70 to 80% of the movement of freight is done with trucks. And given our relatively meager expenditures on rail and on other forms of transportation, it probably will remain the major way that we move traffic for quite a while to come. So if you take a state like Florida, where typically we have rather long highways that cross the state, for example, I-75, I-95, these roads, just like lots of highways, are prone to congestion and prone to accidents, of course. When congestion and or accidents occur, of course, this obviously delays the transportation of traffic, which is always an issue, but that issue has been magnified, of course, through COVID. And now, even though hopefully COVID is beyond us, it's still an issue because we continue to have problems with the supply chain. If you can't get your equipment, your materials delivered on time, that has a very negative impact on your ability of the business to generate a profit. So the interest in this topic came from the need to, first of all, find out or detect that there is a congestion issue somewhere, and then using this information help direct the traffic away from the area of the congestion. It could be an accident or a slowdown or whatever around that congestion, and therefore save travel time and hopefully increase the efficiency of the transportation network in terms of delivering goods and services and so on. So in the presentation I'll present to you, there are basically two components. One component is or has to do with the detection of the congestion itself, and then a separate component that has to do with how does one route the traffic around this congestion. Now, this can be done, of course, using a variety of ways. However, our team was confronted with a rather strict set of constraints that we had to operate under. Cost was a very important issue because we wanted the installation, and we wanted this technology to be used, to be deployed quickly in areas without having to have an already existing expenditure of extra infrastructure to mount sensors and so on. So that was a major requirement. Another major requirement is because of the real-time nature of the required response, we had to have very efficient communications. We had to have communications anywhere. The system had to operate on extremely low power requirements because most of, and this may be unfamiliar to some of you, but most of the highways actually do not have readily available power. Even if you drive on highways and you notice that, well, I can see the signs being lit and so on, a lot of these systems actually only operate after sunset. So in other words, there are issues related to the existence of power. We wanted to develop a technology that can be used easily in work areas. As I mentioned earlier, low cost. We wanted to make sure that it's very low power. We wanted to make sure that communications is included. And finally, we wanted to make sure that we have a solution that is not just low cost, but also scalable, so we can keep adding sensors if we need to without having to change the underlying architecture of the network in this case. So what we settled on was mesh networks operating on microcontrollers. The beauty of mesh networks is, unlike traditional communications, each node can actually try first to communicate to the closest node, which and the architecture of the network can heal itself if one or more of the nodes, within reason, of course, stops operating or stops communicating. So we settled on a microcontroller architecture, extremely low power, operating on a mesh network. We did not go to things like Wi-Fi, LoRa, and Bluetooth because their power requirements are a little bit higher, and there are some limitations as to how quickly the network can heal itself if we need to. Now, we can, of course, collect this type of data, which is primarily type of the vehicle, whether it's a car or a truck, and potentially the speed of the vehicle to detect congestion. We can easily could have done that through Doppler radar. Doppler radars tend to be very expensive, and the infrastructure to install them is rather expensive. So instead of using that, we settled on using individual lidars with just single ray lidars, basically each connected to a small microcontroller running a mesh network. The data is taken, and through the mesh network, which is the data is collected primarily through these collectors that you can see on your right-hand side. The data from the collectors gets dumped into a gateway that you see on the left-hand side, and the gateway sends a rather compact MQTT message to a central server, and that central server will send the information to some sort of a back office where all of this stuff can be manipulated in real time to find out if there is a congestion. Now, because this is single laser, of course, we could not measure speed, but we use the occupancy time with an algorithm to try to detect if there is a slowdown on the highway that points to a congestion or to an accident. I mentioned earlier that we needed to have reliable power. So we designed and installed this solar system, two 200-watt panels, relatively low power, that feeds the various sensors. And this is the system we came up with, very lightweight, easily scalable, that can be connected to existing infrastructure, in this case, overpasses and the like. And again, supplied power, we had some issues because we sometimes the solar panels had to be a good distance away. But anyway, we resolved all of this, ended up with this system and this specific very low cost lidar that had enough power. Remember, we are shooting down on asphalt, so being a black surface, we had to have sufficient power. So we settled on this lidar that's made by Garmin, and you can see on this lidar, you can see on the right-hand side, that is how it kind of looks down on the traffic, and that's how it detects the traffic and finds out if there is an issue. For the second part of this research, as I mentioned to you, we wanted to get this information in real time, quickly detect if there is an incident, and then if there is an incident, develop a way to route the traffic around the network. Now, you may be saying, well, you know, Waze and Google Maps and Apple Maps does this stuff already. Well, that is true, but it does not do it for trucks. Trucks obviously have weight limitations. They have geometric limitations in terms of how much space they need in order to maneuver. They have noise issues. They may not drive through certain neighborhoods. So we took the existing literature, existing algorithms on traffic routing, but then we added to it the constraints that would be specific for trucks. As you can see here, the level of service of the highways, are you allowed there, number of lanes, geometry of the roadway, the speed, what sort of vertical clearance, all these issues, pavement condition, if there are schools, if there are hospitals, all of this type of information may not be necessary for cars, but it is vital when you are thinking about routing trucks around existing issues. So we took all of these and we inserted it into a geographic information system. The geographic information system, we took that and we applied it to the I-75 corridor, or to this corridor that you can see, and basically did some simulations. What happens if there is an incident? As you can see on the right-hand side, there is an accident. This was detected because of the real-time information received from the gateway. Upon detection, it figured out that the best way, given all the truck constraints, is to route it in the way that is shown in the bottom right-hand side. And we did some scenarios, several case studies to try to take this savings in time, if you will, as a result of routing the traffic around specific incidents, and then try to quantify in dollar amounts what would this equate to in terms of time savings. Of course, we can also extend this work to include things like emissions savings, potentially protection of pavement. So there are a lot of potential benefits that occur with a truck-specific routing system around existing congestion. So in summary, we developed a hardware and a software architecture that can be used nationwide using existing real-time operating systems, low power, an algorithm rather smart, working on simple microcontrollers to detect incidents. We field tested that in 2 sites with the help of our sponsor. And then, of course, we included all of that in a GIS-based traffic-specific algorithm, and we studied the potential impact on multiple case studies. Where do we hope to take extensions of this research in the future? We would like to explore the use of miniaturized cameras with optimized AI edge algorithms for detecting, for example, license plates, and use that for origin destination studies. I did do a similar project like that, but this was almost 5, 6, 7 years ago, where there was a dearth of edge hardware. So we had to have computers, and it was very power intensive. Now, with the existence of all of that, I would like to revisit that, and then to look into new low bandwidth, low power and communications approaches, because really my interest in research is for helping our DOTs using existing infrastructure and using existing technologies. Thank you for this opportunity, and happy to take any questions.